We are about to move to another major topic of foundation engineering, that is the analysis and design of earth retaining structures. It's very interesting to point out that the earth retaining structures are much different from what we learned before, that is the shallow and deep foundations. One major difference is that for earth retaining structures, usually the load does not come from the superstructure directly. In some cases, we don't have any superstructures. We only have the soil. And the purpose of building that earth retaining structure is just to support the soil. So essentially, the load comes from the weight of the soil body. So in order to design a earth retaining structure, we need to know how to calculate the load, and we usually call earth pressures. That's the topic of today's lecture. That's earth pressure theories. The objective of this lecture is that you guys need to be able to calculate the earth pressures and their components, magnitude, direction, and position, using two earth pressure theories, Rankine's theory and Coulomb's theory. We will arrange this lecture into three components. First, I want to have an overview of the earth pressures and earth pressure theories, so we can get a big picture regarding what earth pressures we have and what theories we have and what is the relationship between the pressures and the theories. Then we will be talking about the Rankine's theory and the Coulomb's theory one by one. Let's take a look at the earth pressures and their theories first. So it's an overview of here. When we say earth pressures, actually we are referring to the lateral earth pressures. We calculate the lateral earth pressures based on the vertical stress. So that is the widely accepted procedure for doing this. Sigma H prime, or H here means horizontal. So if we use the symbol that we used before in soil mechanics, that is sigma X prime, because X is the horizontal direction. Or if we talk about pressure, we also use P equals K is the earth pressure coefficient. Depending on which theory we use, we have different earth pressure coefficients, times sigma Z prime or Z0 prime. The same thing. That's the vertical effective stress. The sigma Z prime, the vertical stress can be calculated based on the unit weight of the soil above the point of interest and the thickness of the soil layers above that point. The equation can be simply written as, it's a summation here because we may have multiple soil layers above that point. Gamma I HI means the unit weight and the thickness of the ith layer. It's the effective stress. We need to subtract the water, the pressure caused by water. So it's gamma W times H W. So that's how we get the lateral earth pressures or earth pressure. We know how to calculate sigma Z prime using the method for calculating the stresses in the ground. Now, if we can figure out how to calculate K, then we can calculate the earth pressures. For the K, we have different theories. Those are the theories for calculating the earth pressures. So K is the earth pressure, or lateral, to be more accurate, lateral earth pressure coefficient. We have seen three of them. The first one is the at rest earth pressure. Second one, active, passive. These three types of earth pressures represent three different states. At rest is the state without any soil movement. So that's what we have in the ground before we place any buildings on it. Active is the state when the soil moves actively, and the limit state as the soil starts failing. And the passive is the soil fails because another object pushed the soil and make it move away from its original position. So for at rest earth pressure, I showed one equation before, and I mentioned that this equation is very widely used, so it's better that you guys can keep it in mind. So it's the difference between 1 and the sine phi prime times OCR, the over consolidation ratio, to the power of sine phi prime. If the soil is normally consolidated, then this part turns into 1. For active, we have the coefficient K sub A. For passive, we have K sub P. We have Rankine theory that we can use to calculate the active earth pressure. We can also use another one called Coulomb. I've already introduced the Rankine's theory when we are discussing the sliding resistance of shallow foundation. Later on, I will review this theory. For passive, we also have Rankine's theory and Coulomb's theory. I will also want to draw a schematic to show this idea. That is how to get the earth pressures based on the vertical effective stress. Let's consider a very general situation when we have multiple soil layers. Let's say now we have 3 soil layers, and we want to calculate the lateral earth pressures caused by these 3 layers of soils. Because they have different soil layers, so the distribution of earth pressures will not be a straight line. We know that the earth pressures varies with the depth, and the slope is the unit weight. So we have 3 different layers, then we can have 3 different slopes for 3 segments. This is the first layer, second layer, third layer. So 3 layers. And the earth pressure, that's the effective stress along the vertical direction. And we know that the philosophy for calculating the lateral earth pressure is that we get a sigma z prime first. Then we get the earth pressure coefficient based on any of the theories for at rest, active, and passive earth pressures. Then we get sigma h or p equals sigma z prime times, let's use x to avoid confusion, times k. So this is the distribution of the lateral earth pressure. But as we see in the objective, we need to know how to calculate the pressures and also their resultants. So we need to do the force. For the force, we need to know 3 things: magnitude, direction, and position. For the resultant force, we know the magnitude in this case can be easily calculated. It's just the area of this pressure distribution. So let's draw a resultant F here. So F is the resultant, it's a total. And since we are considering only a 2D case, we do not consider the direction that is perpendicular to this piece of paper or this cross section, then the unit should be Newton per meter. So we multiply this resultant with the width, then we will get a Newton, get a force. And this one is the area of the pressure distribution. For the direction, because we're talking about the horizontal pressure, so the resultant of the horizontal pressure should also be horizontal. So it's not difficult to determine that one. But for the last one, position, we need to pay more attention. The position is a relative thing. Usually we need to say the position of this force with reference to a specific point. And here, for example, we can do it in this way. We can use this point. Let's call it the point O. And the position of F can be determined as we know the distance from this point O to F. So that is here, this Z. Z can be obtained in this way. We know that the F is the resultant of all the pressures. So the moment caused by the pressures should be equal to the moment caused by the resultant of the pressures. That is, let's just say that the moment of the pressures, we use a summation sign because we need to calculate, in this case, the moment about point O. So we used M sub O to represent it. And we can do it by dividing this irregular shape into 3 components corresponding to the 3 layers. For each layer, we know, for example, if it's a triangle, for the triangle, we know the resultant is the area of the triangle. We know the location of this resultant will be at the centroid of that triangle. That is 1/3 of the height from the bottom side of the triangle. For the trapezoid, we can do it in the same way. Then we can just add them up. We can get the summation of the moment. That one equals F times Z. So based on it, we can get Z, that's the distance from this line of action of the resultant F to the point 0. So sorry, point O. In this way, we can determine the location of the force F. And this philosophy applies to at rest, active, and passive pressures. For example, the FA for the active pressures and its resultant. We just need to replace the F with the FA. This is what I want you guys to know about earth pressures and the theories for calculating the earth pressures. Based on this understanding, now let's take a look at the Rankin's theory first. But different from what we did before for the Rankin's theory in the analysis of the sliding resistance of shallow foundation, here I want to talk about the Rankin theory for earth retaining structures. So the model that we will use will be a little bit different. We will have a wall. to sustain a soil body. And in practice, this usually happens as we build retaining walls. For the retaining walls, what happens is that we will put backfill materials on the backside of the retaining wall. And those backfill materials, usually they are granular materials, have very good drainage properties, so that the pore water pressure will not build up behind the wall. That will hurt the stability of the earth retaining structures. And because of that, here the Rankin theory that we will be discussing is for the inclined granular backfill. It's a granular backfill, so it's a sand. The cohesion is limited. It is negligible, so we can assume that C equals 0. So let's first take a look. What we learned before. But now we have this model. We have a wall, and then on one side of it we have soil. But what we learned before, we have level ground surface. Horizontal is not inclined. That's the simplest case that we can have. But previously we talked about C5 material. The C5 material, the soil has both C cohesion and internal friction angle. And also this wall is vertical. So you can see that's what we learned before. C5 material vertical, and this one is level. And with such a conceptual model, we can derive Ka as and Kp as we mentioned before. Kp is greater than 1 and it's greater than Ka. That can be easily seen from these two equations, because tangent of 45 degrees equals 1, and if it's less than 45 degrees, then it should be the tangent of it should be smaller than 1. Of course, the square of the tangent should also be smaller than 1. The stress distribution corresponding to active and passive, we also talked about this before when we are learning the theory for designing the shallow foundation with respect to the sliding resistance. The distribution for active pressure for the C5 material would be look like this. We have negative pressure just because we have C in it, we have cohesion. And for the passive, it looks like this. If you have forgotten this, please take a look at your notes for the sliding resistance of shallow foundation. Now we are moving from what we learned before to what we need to know about for this new application, that is the inclined granular material. And difference first, we have inclined backfill, and second one is phi only, so we don't have C. C is negligible. Again, I want to make a comment here. C is negligible for large was. And another reason is that we usually use granular backfills. And if we move from what we learned before to the new application, when we have inclined backfill and when we have a fine material, that's granular backfill, instead of the C-fine material, which has both internal friction angle and cohesion, we will get the new Ka and Kp equations. Here I will not show the deductions, so if you are interested, you can take a look at your textbook. So here I want to show the equation directly. That's because our major interest is about the application of these equations and not about the deductions. So please be careful, especially be careful with the signs. The two equations for Ka and Kp, they look similar. And here we have a negative sign between cosine alpha square and cosine phi prime square. Don't forget the square either. Numerator similar, but here we have a negative sign instead of a positive sign. Fa, if we know how to calculate Ka, then Fa just equals 1/2 times gamma times h squared times Ka. So this equation is the same as the one that we learned before. For Kp equals cosine alpha, you will see that these two equations are very similar. And the major difference between them is the signs. So now in the denominator, we have a cosine alpha. Now it's minus instead of plus. Inside the square root, we will have the same. The numerator, we have cosine alpha, now it's plus. So we have a square second power for each of the terms inside the square root. And Fp also has same equation. So it's 1/2 times gamma times h squared times Kp. That is the Rankin's theory for earth retaining structures. And we add a few things to the theories that we learned before. Now we have backfill inclination, and we simplify the C-phi material into phi material based on the field conditions, because the backfill materials that we use are mostly the materials without cohesion. That's the phi material. Next, let's take a look at the Coulomb's theory. Let's use a new page. And for Coulomb's theory, it's only available for granular material. So we don't talk about the C either. For the Coulomb's theory, now we can consider even more complicated situations. First, the back of the wall is not necessarily vertical anymore. So we can consider a retaining wall with a shape like this. The height of the wall is h. Here I want to show the process of how to obtain the earth pressure coefficients. I will not go to the deductions in detail, but I will still want to go through the procedure so you guys can get the idea of Coulomb's theory, how the active and passive earth pressure coefficients could be obtained. And we also can consider an inclined backfill. And for the backfill inclination in this course, we will use alpha to represent the angle of inclination. In the Coulomb theory, the key to the acquisition of the coefficient is through the consideration of the soil body behind the back of the retaining wall. Here, this is the back. The back is the side with soil. And we assume that if the soil body behind the retaining wall fails, we will have a planar slip surface. So in 2D case, that's going to be a straight line. Let's assume this is the then we will have this soil body. So what's going to happen is that the soil on two sides of this slip surface will move relative to each other. It's a straight line because we assume that the surface is planar. And in order to consider this soil body, here in this plot is a triangle. We call it the soil body or its soil wedge. So we can take a look to see what forces this soil body suffers from. Of course, it has its own weight. So we use W. And the soil body on the other side of the slip surface should also exert a force on it. That's a reaction force. So let's call it R. Because the direction of R, actually we can determine it based on the relative movement of the two soil bodies. Now we are talking about the active. Active means that here, this soil body will move itself. So that happens usually when the wall moves away from the soil body. If the wall moves away from the soil body, then the soil body of interest, that is the soil body above the slip surface, will move downward. So if it moves downward, then the soil body on the other side of the slip surface would, first it has a vertical force to sustain the weight of the soil body above it. It should also exert friction. And the combination of this normal force and friction, like two of them, this will generate this total reaction force, R here. We should also have another force coming from the wall, because the wall needs to sustain the weight of the soil body above the slip surface. There is also friction between the wall and this soil body. So based on the relative movement, this force should be like this. And this force is the resultant of the active earth pressure. Now we also want to determine the angles, the directions of the R and FA. For R, because it's the contact between soil and soil. On two sides of the slip surface, we have the same type of soil. We know that for the friction between the same type of soil, that's the internal friction angle. So here, this angle should be phi prime. And for the FA, the angle here, this angle is caused by the friction between the wall and the soil body, and that is determined by the friction angle between the wall and the soil. So that's delta prime. Location for FA, it's not difficult to figure out that this location actually should be, if we draw a horizontal line, this location should be 1/3 of h. So if we, there's one more angle that we need to pay attention to. That is this angle beta. We call this angle beta. That's the angle of the inclination of back of the wall. So with all the information in hand, we can put the forces on this soil body of interest, that's the soil body above the slip line. Together, we will get the following, the force triangle. So we have weight, and we have FA, and we also have this R. You can see that the three forces should form a closed triangle, and in that case, the soil body of interest will reach mechanical equilibrium. But some of you may ask, we still need to know some other things so we can determine the magnitude of FA based on weight. Because as long as we know the angles, as we know the magnitude of weight, we can calculate the FA. But the problem is that we don't know these angles. We even don't know the location of the slip surface. So to do that, we introduce one more angle. That is this angle. We don't know this angle. So what we do is that we try different values for this angle that we marked with a question mark. And people found that it happens in this way. We try different angles, and we try one angle, we will get one FA value. We try another angle, we get another FA value. And if we connect all the FA values together, we will get a curve like this. The FA value that we want, in this case, is the maximum FA value. So this is the real FA. That is, while we can have many possible slip surfaces, the critical one, the most possible one, the critical surface corresponds to the maximum FA. And the people have already derived the equation for calculating the FA, the maximum FA. Accordingly, the K sub A can be calculated using this equation. So we don't need to know how to derive that, but we need to know there's the equation and know how to use this equation. The numerator is sine beta. So beta again, that's the back inclination, plus phi prime squared the denominator is sine beta squared times sine beta minus delta prime. Delta prime is the friction angle between the back of the wall and the soil in contact with it. And there's another term in the denominator. We put all of them into a pair of brackets. So please pay attention to the signs and the powers. We also have alpha here. Alpha, that's the backfield inclination. Then the thing inside the brackets to the power of 2. And FA game is obtained using this very simple equation for a phi material. For a C5 material, it's going to be more complicated. We're going to have another term for C. This is for active earth pressure. And we get the K sub A like this. So please take a second look at this equation. Make sure you copy it down, the correct equation. Then let's take a look at the passive case. The process is similar. I'm going to draw the same thing, the same wall, and also a inclined backfield with the inclination angle of alpha. We also have the wall, the thickness is h. And what we do, just consider the static equilibrium of the soil above the slip surface. But you may find that for this slip surface, usually this angle of inclination is smaller compared with the active case. So this angle, I put a question mark here, smaller. We don't know the exact angle. Here we have the soil body, the weight is W. And there's one major difference between the active case and the passive case is the tendency of the movement of the soil body of interest. In this case, it's passive. So what happens is that the wall pushes against the soil body of interest. And because of that, the soil body of interest will move passively. So the direction of soil movement will be upward instead of downward. And because it's upward, now the direction of friction will change. Here, if the soil body wants to move upward, then the soil body below the slip surface will put a friction like this. So because this friction and also have a normal force, we put them together, we're gonna get a R like this. This is R. And now this angle is phi prime. We said that is because it's friction between the same type of soil. Due to the same reason, if we take a look at this F, now the FP is going to be like this. And this angle, again, is delta prime. It's FP. The point of action is 1/3 of h from the bottom of the wall. and this angle is also beta. So if we put all the forces acting on the soil body of interest together, we will get the following triangle. This is W, and R is like this, and F is like this, FP. So you can see that they form a closed triangle. Again, we don't know the exact value of this angle of this slip surface. So what we do is that we try different angles for this angle marked with the question mark. And what we would find for the passive earth pressure is that we will get different points. And if we connect the points, we will get a curve. And we found that the most possible angle is the angle with the lowest FP value. So this is the FP, the most possible FP. We know the FP, we can get the KP. Because KP, we know FP, we can calculate the PP. We know PP, we can calculate the KP. KP is, you will see that the equation for KP is very similar to the equation for KA. Let's start with the numerator. It's the same sign, but here's beta minus instead of plus 5 prime squared. In the denominator, first is also sine beta squared times sine, now it's beta plus theta prime, not a minus anymore. And we have another long component inside a pair of brackets. Now let's see, 1 minus square root of a fraction. For the fraction, the numerator is sine 5 prime plus theta prime, the same, times sine. Now there's a minor difference. That's 5 prime plus alpha. In the denominator, we have sine beta. There's a difference here. It's plus theta prime times sine alpha plus beta. This is the same. Then adding the right brackets. Don't forget this 2 second power here. And with this KP, we can calculate FP. So it's similar. It's 1/2 times gamma times h squared, now times k sub p. Oh, let me add a few things here. The soil body is moving downward, so you guys can see why there's a difference. And this soil body is moving upward. This is the Coulomb's theory. The key again is the equation for Ka and the equation for Kp. As long as we know these two lateral earth pressure coefficients, we can calculate the Fa and Fp. That's the loading for designing earth retaining structures.
I think I'm falling for you.